Good afternoon. So I'm a big fan of user-defined literals. I want to give a nice 1-hour talk on how wonderful these things are because I use them all the time and I see them, I think they're underused. And so I was putting together this pleasant 1-hour talk when I came across Google's C++ coding standard. And I thought it was a little over the top. They basically said, you know, if you use these things, you are morally deficient in some way. And then there was a blogger who said, yeah, they look useful. They look really neat, but all I do is make your syntax better. Well, yeah. Oh, I'm sorry, I didn't introduce myself. I figure you can Google me for the next 15 minutes, after which, you know, I'm not going to be nice to Google. Okay, so type syncs are a real problem, right? If you have a date class like this, what's going to happen to you? You're going to die. There's no question about it. There's no way you can get the dates right, especially if you are dealing with, you know, Americans, Europeans, programmers, Martians, whatever. They all have different date standards. You'll just never get it right. So obviously what you want to do, by the way, this is a 1-hour talk, so I'm speaking twice as fast as usual. If you want me to slow down, leave. So of course what we do is a little reification here. We create a type that represents a day, a month, and a year. We all know how to do this. And now we can create a nice date class that is properly initialized, and you just simply can't get wrong. It'll either work or you'll get a compile time error, which is what we want. And we could force people to do things our way, or we could be proper, civilized people and let people have their own way of doing things, but still get a correct result. In my other life, I'm a Democratic campaign manager. Yes, I will argue about it. Not now, though. The trouble with this is it's still not all that great because we have what Scott Myers called C++'s most vexing parse. You can do something very reasonable like this, and unfortunately, C++ is inherently ambiguous. You've noticed how twitchy C++ compiler writers are, how they look nervously around them all the time, like they're waiting for another non-terminal to appear in the language. And that's because you can't actually parse it. It works pretty well anyway, but it's nerve-wracking because this is actually a function declaration. It looks like an object declaration, but it's not. The compiler looks at this and says, oh, you don't need these parens. They're gone. Now it looks like a function declaration. To fix this traditionally, this is the greatest fix in the world. Throw in even more parentheses. So many the compiler can't ignore them anymore, and it has to treat it like that. It's kind of like when you want to have a correct declaration of a pointer. If it doesn't work, what do? Throw another star in there and see what happens. Eventually, it's going to compile. The compiler will just give up. So in the base language, we have this really nice facility. We can take 39, which is an integer. If we don't want an integer, we can make it unsigned by attacking on a u. We can make it long or an unsigned long. We can change the type of a literal just by attaching a different suffix. And this is great. It's almost like cheating. And cheating is a good thing in politics. And so what we want to do is have that same capability for our own literals. We're not just interested in unsigns and longs and things like that. We want to take these numeric and non-numeric literals and make them generate our types, our user-defined types. So a user-defined literal is just a literal, which can be parsed as a literal, followed by a user-defined suffix. And we can define this with a literal operator. And if you haven't seen this before, it looks a little strange, but you get used to it. You've gotten used to a lot already, right, in C++. So what's a little bit more? So this literal operator is operator, double quote, and then an identifier. And the standard wants us to start our identifier with an underscore, strangely, because other names are reserved to the implementation. So if you want to have an operator go to, you're not allowed to. You can have underscore go to, but not a go to. But we'll see that we actually can use keywords in this context and that we shouldn't. So here's an example of a day user-defined literal. Here's my operator double quote, the user-defined literal, the user-defined suffix is underscore day. And it's a simple const expr function. As most of these are, most people want their literals to be compile time constants. By making a const expr, it'll be constant enough in most circumstances. And all we do is return a day, and we're done. Very simple. And we have a cast in there to shut the compiler up. Notice the type of the argument. It's the largest integral type in the base language. So when I produce an integer user-defined literal, I have to declare the argument to be that type. Not int, not unsigned long, but unsigned long, long. We have no choice. And that's because the compiler is going to be parsing an int and giving us that value, and we have to be prepared to take an arbitrarily large value, even though, once you get past a couple hundred, it's probably not a good value for a day. So again, we can fix this gotcha by being much too clever, or we can be modern, or it can be very modern. So I suggest that this is probably the clearest way to write that declaration. I can say month, day, and year. I can say month, year, and day, the way they do on Mars, and so on. So it gives me flexibility. It's also readability. And we need all the help we can get with C++. What about negatives? I brought this up because a lot of people bring this up. Well, the negative sign is not actually part of the literal. If you look at the standard, I know you all have a copy of the standard. I can tell by your upper body strength that you carry it around. You'll see that the negative sign is not actually part of the literal, and so we actually have to, if we want to have negative days, we actually have to overload that negative for our day type. So it's associated with a type, not with the user-defined literal. Everybody okay? Because you look kind of upset. What about money? It's time we talked about this. Well, money is kind of scary, actually. I used to write compilers for a living, and then, after I got out of therapy, I decided to do something less stressful, and I decided to trade derivative securities. And when not myself, I was using somebody else's money. Do I still do this? No. Why? Don't ask. And I worried about, well, how do you represent US dollars? Double. How do you represent Canadian dollars? Double. What about francs? Double. We still had francs. And so this made me worried. So I thought it'd be a good idea to have money, and just define money very simply, and probably improperly, as just a variable amount of a fixed currency. So this will prevent mixing and matching US and Canadian dollars, which is too bad, because you can make an awful lot of money by buying, Canadian dollars on a good day, on a bad day in Canada, and then just turning them to US dollars. But we don't want to do that. So what we can do is provide user-defined literals for each of these currency types. Now, this is going to be a floating point literal. And in that case, the standard requires that the argument be a long double, the largest built-in floating type. And we can't change that. We must accept the long double, because again, the compiler is going to parse and evaluate a floating point literal and pass it by value as a value to this overloaded operator. But these are very, very simple functions. It could perhaps, you could throw in some error checking if you want, but you don't have to. C++. So with this in place, we can actually write a readable declaration. I claim that this is much more readable than the previous version. This looks so 2000s when you look at it. This looks like a truly modern declaration that even Scott Myers would approve of. You can have scientific notation. It parses a long double, and hands you the value. Yeah. And if you want to, going back to the days, you can write your days in base 2. If your Martians do. I've never been to Mars. I want to. So this gives us even more choices. Nikolai Jasudis was quite upset a while back because there were more than 30 ways to write a declaration with an initialization in C++. Here's another one. But I think this is actually helpful, because let's look at, these are really old-fashioned declaration. It's so gauche, right? You're actually saying the type of the thing you want to declare. Well, we can avoid that by using what Scott Myers calls the explicitly typed initializer idiom, which means take the information here and push it over here. That's okay. No, there are some good things about this because I get to use auto, so this is guaranteed to be initialized. Scott won't yell at you. There are all kinds of good reasons for doing this. But I claim this is even better. I think this actually is a readable way of rendering this declaration. And so the user-defined literal does help us in that regard. So there are actually 6 different kinds of user-defined literals. These are the cooked literals. They're cooked because the compiler not only parses the literal, but it evaluates it and gives us the value. We've seen a floating point literal, an integer literal. We can also do character and string literals. The string gets the string, which is null terminated, plus a length of the string. And these can be various character and string types. So for instance, if I were to write something like this is simply calling this operator. By the way, of course, just as with all the other operators, you can call these literal operators directly. Why? But you could. Here's a string literal. This passes the string plus the length of the string. Okay, so I am moving rapidly. If anybody, seriously, if you want me to repeat something, see me after. So here's a stock. This is the worst designed stock on the planet. You can initialize it with a ticker, a numeric QSIP. QSIPs are alphanumeric, but if you have a numeric one, you can use it. Or a single character ticker. I know, everybody has a bad day. This person had a monumentally bad day. But nevertheless, this is now in use, and we have to support it. So we're going to overload 3 different user-defined literals. We'll have a character string literal, a floating point literal, and a single character literal. And we can overload the same UD extension for all 3. And again, this is very simple stuff. And overload resolution will disambiguate for us. So we can recognize a ticker, a numeric QSIP, or a single argument ticker. Extra credit if somebody tell me what F stands for. Ford. All right, so everybody knows that. Well, what's AT&T? Okay. So you guys are in the same boat I am. You've lost so much money in the stock market, you have everything memorized. You can also, the standard library does this too. S means standard string in the context of a string literal, but it means seconds in the context of an integer literal. And I actually disagree with this because, this is the only time I agreed with Google on this. I like them generally, but the coding standard is written by somebody who's had a really rough life or something, because they just ban everything. So don't code in C++ except how we tell you to. Anyway, I think it would be clearer if we did this. I mean, we don't even need a comment now. Is this a string? Yep, it's a string. This is seconds. So I would suggest, to the extent possible, the UD suffix should be associated with a type returned by the literal to make things a little bit clearer. I mean, after all, this could be not seconds, but something else. Seagulls?
Seagulls, S-E-G-O-L. The European QSIP.
Oh. I'm having enough trouble up here. Okay, what about slugs? Not the things in your garden. This is a unit of measurement of mass in English units. And English units are great because they're really natural. Like furlong, that's the length of a furrow. It's almost the same thing as a stadium, a little bit longer than a stadium. So that they feel good if you grow up with them. But when you're doing physics, if you have to do something in rods per fortnight or something, it gets a little clumsy. So nevertheless, we might want to support these things. So I have a slug, so I'm going to have a slug user-defined literal _slug. Now, of course, if you're into land-based mollusks, this could be confusing, but most of us know we're referring to English units of measurement. And so this works fine. This floating point literal, if you go back here, you'll see this is a floating point user-defined literal. It works fine, but this, unfortunately, we will not attempt to look for an integer user-defined literal. So it is probably a good idea in this case to do an additional overloading and just forward it to the floating point version. So this will fix that particular problem. Let's go back to our dates. Is this a good idea? We had day, month, and year types. And of course, we have a date type. Should we have a user-defined literal for date? Notice the quotes. If you haven't been programming in C++14, now you can use quotes to make your numeric literals clearer or not, depending on how you use them, because you can put them anywhere you want inside the literal. But this looks pretty clear, right? This must be a year. Is this a day? Maybe that's not a month. So in this case, but we're going to do year, month, day, because that's the way it should be done, right? Yeah, it sorts, right? The trouble is we're getting the value here. We're accepting an integer type, and so we might get this, which is what we want. This is not so good. This is, oh, ouch. How many people feel warm things about octoliterals? Yeah. Binary literals, great. But we used the quotes really well. We broke it up into 6 bits because when you're programming on a cray, you know, in the mid-70s, whenever it was, it's very handy. Okay, so what we'd probably like to do in this case is we don't want to give people too much freedom, just enough freedom so they can do what we want them to when we're programming. Politically, I feel differently. I was warned, oh well. So we have what are known as raw literal operators. They don't get a value, they get the characters of the literal. And now we have full control. There are 2 kinds, raw literal operators. There is a raw literal operator, which is fine. It gets a character string of the actual characters. And we have a literal operator template that gets the same information as a pack. So you can probably guess which one I like. I just talked for 2 straight days about templates. Templates. Templates are wonderful. So here's an example using the literal operator, the raw literal operator. Say we want to parse things in base 3, as we all do. We can actually do it like this. We can get the characters, and in this case, it is almost certain that this string will be a compile time constant. This is a literal, so this will be a valid const per function. And we can probably calculate the value at compile time, doing some sort of simple thing. Const per functions from C++11 to 17 are like different beasts. You can do almost anything now with a const per function that you can do, that you want to do. Changes to the const per function themselves and the standard library just give us so many tools that we can do a lot at compile time. And so we can take something like this and translate it into base 3, and it could be a const expert. That's nice. Some little bit on the suffix details, things you may not know and are probably happy that you don't. But the standard says very carefully that names that don't start with an underscore are reserved to the implementation. And of course, you know that underscore capital letter is also reserved to the implementation. But we can do this, operator underscore. That's nice. This is operator 1, 2, 3, 4, 6 underscores. I don't recommend it, but you can. You can also do this. This is a valid identifier. By the way, this is the name of a song from 1962, I think. Beechwood 45789. You guys are not into the 60s? Well, you had to be there. So here's 42, and it always returns 42. All right, this is probably a bad idea, right? No one would ever do that. But the point of C++, why is the language so complex? Why is the standard 1,800 plus pages going for 2,000? Actually, C++ 20 is actually 2,000 pages in the standard. Well, it gives us capability, and it's not hard to program in because we don't program with the language. We program with idioms and convention and so on. So the job of the language as a substrate for that is to be flexible and useful. So you can do things like this. If you're like me, I never can deal with standard bind. I always get everything wrong. So I want to have comments in here. So what I'm going to do is use a literal, user-defined operator to redefine these placeholder types. So _1 is going to be a suffix that returns _1. These are two different _1s, by the way. So the nice thing is that now I can write this. I have little comments here next to my placeholders. Now, this is not really a recommendation, but the point is we want this flexibility in our language so we can do things like this where it makes sense. It doesn't always make sense, but that's no reason not to do it. Here's a nice thing starting in C++ 14. We can have an underscore capital letter at the start of our user-defined literal, provided we don't have a space between the last quote and the start of the suffix. And when I first saw this, I was thinking, what? Well, I say that a lot when I'm reading the standard. But the nice thing is, now we can use capital letters. And a lot of user-defined literals are going to produce things of a class type, like this QSIP to stock literal. And our class types usually start with uppercase letters in civilized programming standards. So now we can do that. We don't have to say lowercase stock. We can say uppercase stock. This is the type that's being returned. That's a little bit clearer. We can also use keywords, of course. We can have an operator auto. So you can write things like this, auto Ford equals Ford auto. Now, the good thing about this is that only this is not available to mortals. It's only available to standard library writers. But eventually, it's going to be quite useful. The only thing in the standard library I can think of that uses this is a floating point implementation of an imaginary number. So this if is not a keyword. This is a user-defined literal. But in the future, we'll find other uses for it. I choose not to explain that slide. So Google should be a little bit happier now, right? Now, instead of writing _date, people's wondering, well, is this type going to produce a date or a date? We can say it's going to produce a date. So that's a little bit clearer, a little bit nicer. But I'd like to talk about literal operator templates in the 5 seconds remaining. No, we have 7 minutes. The nice thing about this is it actually gets the characters that make up the literal. The other nice thing about it is it's a template. And once you have a template, you can do anything you want. You can do good, you can do evil, and it'll be very efficient. So here's an example. We actually just get the characters. And the format of this is fixed. This is the only template parameter you can have. No arguments are allowed. So if you want to do any really cute template meta programming, it has to be done on the return type, because that's your only choice. So here's a pretty simple one. Len, it tells you how many characters you got. So in this case, it will count all of the characters, not just the numeric ones, but also this quote that we stuck in there for no good reason. And again, this works for floating point and integer literals, and that's all. This does not work for character literals. So this will compile, this will compile, this will fail to compile. So why is this important? I'm going to skip over this, I'm sure. Just a couple of restrictions there. So why do raw operators matter? One is syntax. You might want to enforce a given syntax on a user-defined literal. So we saw before that we probably don't want to have a dead beef date, although I've been described that way. We want this format precisely, and we'd like to enforce that. But in this case, we can't enforce any particular format because we are getting the cooked value of the literal. So what we'd really like to do is have the characters. And now we can actually get the characters here, and we can confirm in the implementation of date that the format of this is correct. And since C++ 17, anybody can write this to produce a compile time constant. It's just really easy because we write const expr functions. We used to have to do, fancy character packed nested indexing, whatever, at compile time. No more. We can just write a function, and it'll get us the right result. The other reason we like user-defined literals, literal operator templates, is that there are limitations in the base language. I mean, this is a pretty big number, but it may not be big enough. I mean, this will probably not compile, because this is going to overflow most implementations of a unsigned long. So if we want to have a lot of slugs, we're measuring the mass of the universe or something like that in slugs, this is not going to work. And also, you could have some user-defined types that are quite large, and we want this to actually compile. So the nice thing, again, this will fail, but here we'll get the actual characters. Now, I actually haven't done this for uint 512, but I had a nice implementation for uint 128, and it works fine. You can parse extremely long numeric literals, and everything works fine, and you can do it at compile time. So that's great. Literal operator templates versus raw literal operators. Well, there's a slight difference. I mean, chances are this is going to be a compile time constant, but not necessarily, because I could call the literal operator, sorry, the raw operator, whatever it's called, with a runtime value like this. So this is weird, but it's legal. This is less weird, it's also legal. But the thing is, because this is not necessarily compile time constant, I can't use a static assertion in the implementation. And that's just very irritating. But a literal operator template, this is a parameter pack, a character pack. It's guaranteed to be a compile time constant, and I can use static assertions on it. It makes things a lot easier to write. How would you catch this in a situation where this is not necessarily a compile time constant? You could throw an exception. Starting in C++ 14, you can use an assert. In both cases, your compiler is going to say abusive things about you because you have a no except here. It'll say, you have an exception in a no except function. What's wrong with you? And they get really upset. So I'd rather just avoid that. You don't want to get into an argument with your compiler because it's already a strained relationship. So I really do prefer the template version. Now we have very few options for using Svine in a situation like this. We can't use it here. This is fixed. We can't add additional arguments. We have no arguments here, so we're restricted to the return type. But you can have conditions here. Here I'm using enable if for some compile time condition, and if it succeeds, then this function will have a return type of date. If it fails, it'll fail substitution, and maybe I can overload on a different implementation of date. So if you want to support various different date formats, you could have a whole bunch of them and then enable one or the other depending on your locale or something like that. Here's another example where another reason to prefer templates is there's really no reason to prefer a raw literal operator now, because basically whatever you can do here, you can also do here. Recent changes in C++ 17 to our standard library containers make it trivially easy to basically turn this, turn the character pack into a very usable compile time data structure. So I'm template centric. Now what's Google's problem now? They say it's hard to use an abstract data type and not also use the user-defined literals the author of the data type wrote to work with the data type. Kind of like not being able to use the overloaded operators. It's kind of like saying, yeah, we want the class, we don't want these overloaded operators, we don't want the literals, and I don't even like all these member functions. Why do I have to take all the, some people just are never happy. So how do you deal with this? Well, I would just call up the person who wrote the class and say, these are stinky operators, I don't want them, take them out. That's one thing you can do. Or you can, what the standard library does is it sticks the user-defined literals in a nested namespace. So we have to say we want to use them. Now this is an inline namespace. So if I said using standard string, I would also get the operators. But simply by doing this, I can get the operators, the user-defined literals, but I still have to specifically say I want string. This seems to be a very reasonable way to solve this problem, but Google's not satisfied. So one thing we might want to do in the last 8 seconds we have here is show how we can use a literal operator template to basically provide 2 versions. One, if you want to use a particular operator, here's an underscore hash that gives you a hash value, and the other if you don't. You get to pick one or the other by choice at compile time. So going quickly, all we have to do is provide a spine condition. And here I'm using a trailing return type to show that I am modern. But I could also put this up here. And basically, I have a condition. If the condition is true, then this will be enabled and this will be disabled. If this is true, then this will be disabled. So I'll either get the I want to use hash version or I don't want to use hash version. And I can implement this. And again, this is unfairly quickly, but here's something that declares a variable template that is false. This is a primary variable template. Now, we can specialize variable templates the same way we can specialize class templates, and unfortunately, function templates. And here is the hash condition. It is defined by something that is always true. The size of characters is always going to be non-zero in a literal operator template, because you need at least one character there to parse the template correctly. And we will provide a complete specialization if we want to use this, if we want to enable this hash. So here is a complete specialization of this variable template. If this is not present, this always gives a false value. If this is present, it will give always give a true value, because the complete specialization will be referred to the primary. The session is over. But I'll just say, here's a macro. I don't like macros, but whatever. There's a macro that makes it easy to write. And now you can say this, include hash, include date. I want hash, I don't want date. This will work, this will make a compile time error. Problem solved, so much for Google. This is not perfect. We really do want to have more refined uses of this. We might want to include namespaces in this as well. And we'd also like to make sure that all user-defined operators can be templates, because templates are just very useful. We want to be able to overload them in a variety of ways. So use user-defined literals. Literal operator templates are your go-to literal operator, and they should make your code easy to use correctly and hard to use incorrectly. So thank you.